Hello Internet, my name is Quinn and this is Blondihacks. I'm working on my Pennsylvania A3 switcher locomotive this week and we're going to make the smokestack, or rather we're going to start on it because it's a very complex piece with compound curves and a lot of very tricky setups. So this is going to be a two-parter. I'm excited, let's go. Here's our smoke box so far. You can see the big thing missing on top here is the smokestack. And it's going to be about 4 inches high, something like that. And most importantly, it needs to sit around this hole, which of course is on a curved surface. So that's going to be our key design challenge. The design that Kozo came up with for this chimney looks like this. It's made of 3 separate pieces, only 2 of which are shown in this drawing. And it may look straight, but in fact, it's actually tapered both on the inside and on the outside. The outside taper is for aesthetics, but the inside taper is functional. Smokestacks or chimneys are a great example of the history of engineering wherein people figure out something that works, but they don't necessarily understand why it works, and it might take generations of science to catch up to figure out why the thing actually works. Moreover, though, along the way, we come up with various alternate explanations that we think might be what's happening until we get better and better science to often refine or disprove those earlier theories. Smokestack design is a great example of this. We figured out pretty early on that height is very important on a smokestack. Generally, the taller the better, but also that the inside should be tapered, because a tapered smokestack flows better and thus creates better draft underneath it inside the smoke box. Why does a tapered smokestack flow better? Well, I was interested in that, so I dug into it a little bit. And you know that expression that all models are wrong, but some models are useful, and this is a classic example of that in the history of engineering. There have been multiple theories over the years, 3 major ones. The first, in the 1830s, they believed some version of a story wherein gases required a chimney to be the same shape as they naturally took on when released into the air, so they would kind of measure the shape of the cone of the smoke and match the smokestack to that, maybe not really understanding why they were doing that. Then in the 1850s, that explanation changed, depending on which sources you read, to some version of the gases, quote, wanting to expand outwards in a certain ratio to how much they expand upwards. And if you don't match that ratio, then it creates some unspecified back pressure for unspecified reasons, which interferes with possible optimal flow. Nowadays, we have the actual understanding of why this is necessary. And, well, the answer is, of course, fluid dynamics and calculus, and my calculus is not good enough to understand this sufficiently to explain it to you, but, well, you can look it up if you like, and you'll quickly get buried in terms like vortex shedding and oscillation resonances, and, well, like I said, a whole lot of math that I dropped out of calculus too soon to understand. As an aside, if you ask model engineers why this is necessary, you'll get versions of all 3 of those answers, generally leaning towards the 19th century ones, because that tends to be the information that gets passed on among model engineers. And, well, they're all, like I said, various versions of wrong, and we actually have the science today. We know why this works. Sub aside, if you want to understand the world, learn calculus. It has an incredible ability to explain everything around us. It's really, really remarkable, and I'm constantly reminded I should have taken more of it. Sorry if that was unsatisfying, but that's all I have for you on that. We're going to start today with this base piece right here, which is, as you can see, quite intricate. It has a compound curve on the outside of it and a curve on the underside to sit on the top of the smoke box. I dug through my bins and found this nice piece of brass that should serve the purpose. I'm glad to use this up. It was a tricky piece to use up otherwise. It's not very thick, and it has a big ugly half-threaded hole in the middle of it, and I wasn't sure what I was going to do with it, but today is its day to shine. So I'm going to start by facing off one side of it, as is tradition, of course. Get ourselves a reference, and I'm going to flip that over and create a parallel surface on the other side. And these surfaces do need to be parallel for reference for future setups. So I'm going to take my time here and try to do this as best I can, which in this case turns out to be some parallels on the face of the chuck. And then I'll clamp the piece up against those and lightly tap those down against the parallels. If you tap it down not too hard, then it's up against the parallels and valid, but you can still pull the parallels out without scratching up the piece on the backside. Obviously, don't start the lathe with those parallels in there, or else you're going to be having a very awkward conversation with the emergency room doctor. I should say my order of operations here is taken largely from the book. Kozo has extensive suggestions for all these smokestack components because they are tricky, and I was happy to follow his advice for the most part. I don't deviate substantially in any way. Now, with that thing faced down to final thickness and parallel on front and back, we can proceed to some of the trickier setups. First of all, I'm going to bore out the center of this to a parallel bore. This is still parallel at this point because this base piece slides over the outside of the bottom of the smokestack, and they get soldered together to form what will appear to be one compound shape in the end. So this bore is parallel, but it's going to be one of the only bores that is. And in fact, this has a little step inside it, so after turning that first bore, I'll turn a second diameter a little bit larger, creating a little bit of a shoulder in there, and that's what's going to seat this base piece in position. It's going to locate it on the underside of the smokestack. Took a little bit of time here and care because I do want to hit these dimensions. It's going to help with future setups if all of these dimensions are as accurate as I can reasonably get them, even if in the end none of the dimensions of the smokestack are all that critical. The assembly needs to go together nicely in order for these setups to work, as you'll see. But that is looking really good. I'm happy with that dimension, so let's move on. Now I'm going to take the piece out and I'm going to put this scrap of aluminum in there because I'm going to make a mandrel to do the rest of the turning on that piece from this mandrel. So I'll face off the end, of course, as is tradition, and I'll turn this down to a step profile that can be used to clamp the internal step bore. Now, clamping on a step bore is interesting because you have to get the dimensions just right. The internal step on the mandrel has to be shallower than the one on the part. Otherwise, when you try to clamp down with the bolt, it's going to bottom out against the back shoulder and the internal shoulder, and the bolt isn't actually going to clamp it. And if you're not careful, this effect could be subtle. It may feel like the bolt got tight, but your grip on the part won't be good. Just to be safe, I've made that plenty short on the inside, and you can see it's a little short on the outside as well to ensure that the only clamping that occurs is against the front of the piece and the far back shoulder of the mandrel. Now I can drill and tap the front of that for the clamping bolt. Quick test fit on there. That's looking very good. I'm very pleased with the fit I got on there. It's extremely close fitting, which is good. It's going to help us later on. And for a clamping plate, I grabbed this kind of washer-like thing out of my aluminum scrap bin. Click. And that ain't going nowhere. Regular viewers will recognize that aluminum washer thing from a previous video. If you know what it is, comment below. Or don't, whatever. I'm just making videos here. I'll turn the OD of this now down to the largest diameter of the outermost compound curve of this base piece. It's a little bit tricky to wrap your head around what this is going to be, but hopefully it'll make sense as we go along. Now I'm going to scribe a kind of a line of no return on here. This is where the first curve that I cut has to stop short of. I can't go past this line or else we won't be able to get the correct shape. It'll get too thin at the end. Now I'm going to put an initial radius in the top part of this piece, and this is just kind of a starting point for the future shaping that's going to take place. This is not the final radius, but it's a decent approximation of it. In fact, this radius is a little bit on the small side. I didn't have a large enough radius tool for what the drawing seems to want, although this radius is actually undimensioned in the drawing, but you can kind of get a sense of the scale of it from it being a scale drawing as it happens. So I kind of eyeballed this, doing a couple of passes, and got something that looks reasonably close to what it's going to be, but again, this is just a roughed-in shape, and we're going to be doing a lot more refining once the entire chimney assembly is fully together at the end. It's starting to take shape now, but we've got quite a bit more to do. I'm going to do something that might seem strange at first, but I'm going to part off the end of my mandrel now. It turns out the end of this mandrel is also the exact thing that we need for clamping this base piece in a future setup. So now it's kind of like a T-nut, a cylindrical T-nut, if you will. It's got a little bit of a shoulder on the top, and we're going to need that later. The next cut to do is the curved one on the underside, which allows it to sit on the top of the smoke box. If you've been watching this series, you'll recognize it as being very similar to the one that we did on the top surface of the inner bushing on the smoke box. And I want to talk about that a little bit because I got some weird comments on that one. Well, not weird, but de rigueur for my channel, I guess. Some angry folks questioned why I did this setup to make that curved cut, and they were alarmed by it not because of the ridiculous ill-advised 4-jaw chuck setup, but because I was doing it on the lathe instead of, for some reason, using the rotary table on the mill. And I think this is a failure of imagination that I often see with new folks to machining, or people who enjoy machining YouTube but have perhaps not worked in a shop themselves or don't have experience with the machinery. I think people in general overestimate the capabilities of rotary tables and underestimate the value of lathes. And in fact, if you haven't seen a lot of 19th century manufacturing, when factories used to look like this would have been in fact the normal way to do a feature like this. Although it would have been done on a faceplate, not with a silly 4-jaw setup like I've done here. But this was the typical way that things were done in the world of manual machine tool manufacturing. I guess this is one of those things that's difficult to explain if you haven't tried both methods, but using a rotary table for this would not work very well. You're talking about a very large surface side milling cut, so you'd need an enormous end mill. You'd get weird deflection. You would have chatter issues. Rotary tables are very, very slow to crank, so you're not going to get a nice finish. It's also a multi-point cutter, so you're going to struggle with finish more. Your dimension is going to be more problematic to hit because it's a multi-point cutter and a side milling cut. The bearings in a rotary table are not nearly as good as the one in your lathe, so you're going to have complications there. Rotary table setups are very slow and very time-consuming and very difficult to get accurate. So there's a lot of little reasons like that why rotary tables are just not going to be the best way to do something like this. Maybe people have this idea because nowadays factories look like this, and the calculus for what's going to work well and what isn't is very different. A rotary axis on a modern CNC milling machine is a completely different animal than a rotary table. Even though it may look superficially the same, it has much more in common with a lathe. And since model engineering techniques are fundamentally 19th and early 20th century manual machine tool techniques, we use the lathe for things whenever possible. Short of creating large flat surfaces, the lathe is pretty much always the best machine to use for something if it's practical to do so. I don't know if that answered any of the questions that people had about that, or maybe preempted some that are going to happen now, because I'm going to do a very similar thing right now. This time I am going to use the faceplate, and we're going to create that large concave surface on the bottom of this part. I'm going to use the mill, though, to set up my faceplate, and I think it'll be a lot easier. There's other ways you could do this on the lathe itself, and Kozo describes a method in the book that works just fine, but I like to do this kind of thing on the mill because the mill has a DRO on it, and it makes this much easier. I'm going to dial in the center of the faceplate, which will then be the center axis of rotation of the lathe, of course, once this is mounted. That's going to be my 0, and I'm not going to touch that. Then I'm going to go over to my scrap bin, and I'm going to grab a handy piece of 2-inch angle iron. I think it's actually 1.5 inches, something like that. And I'm going to use this to make an L bracket that I'm going to be able to bolt to the faceplate to hold the part. This is hot rolled plate, so it's not especially square and has a lot of mill scale on it, things like that. So we want to clean it up and make it into a proper fixturing component. So to do that, I'll use the shaper. You could do this on the mill, of course, up to a point, as you'll see. Start by creating an edge there that's nice and square that I can clamp to, and then I'll flip it around in various orientations and square up various surfaces relative to each other. I'll zip through this a little bit, but you can kind of see what I'm doing. I'm cleaning up every surface except one that I didn't need to, and in order to create square surfaces, opposite surfaces that are parallel, and surfaces that will be valid references for future aspects of this setup. I've chosen to do this on the shaper, not just because the shaper is fun and I'll take any excuse to use it, but because the shaper can do one cool trick that is quite difficult to do on the mill, and that's mill up to a tall inside 90-degree corner, which happens to be exactly what one of these cuts needs to be. On the shaper, I can simply rotate the tool around until I have clearance for the tool head on the inside, and I can cut right up to that inside corner. On the milling machine, to do this, because the spindle is going to interfere with that vertical section, you'd have to use a very long end mill, which isn't going to be rigid. It's going to be a difficult cut, or else you have to use a huge end mill. You're going to have to take light passes. You're going to have deflection issues, finish issues, etc. But the shaper, no sweat. Simply tilt the tool over, and away you go. I've got it tilted over pretty extreme here. You got to be careful not to get outside the geometry of your tool when you do this, but these are very light cuts because I'm just trying to clean them up, so I'm still within the nose radius of the tool, and the angle doesn't matter very much. As you've no doubt surmised, this bracket is going to get bolted to the faceplate, and it's going to hold the part at 90 degrees to the lathe so that we can cut that curve. Now, 4 things have to be true all at the same time. This part has to be perfectly square to the lathe, of course, which is why we're machining this bracket, but also the part has to be the correct distance from the center of the axis of rotation on the lathe for the radius to be correct, and the part has to be perfectly square to that axis of rotation, and it has to be centered on that axis of swing. So 4 things. The first one we've eliminated already by machining the bracket. The other 3 all have to be done on the faceplate setup, and getting 3 variables to be true at the same time when they're all interdependent in a machining setup is just about impossible, or it's very, very difficult. However, getting 2 things to be true is quite simple. We do that all the time. For example, dialing in something on the forejaw and getting it straight in the jaws. You might have to go back and forth a couple times, but you can get both things to be true. So the secret to a setup like this is to isolate one of the remaining 3 variables so that you can do no more than 2 things at a time. And I'll show you how I'm going to do that. I'm going to start by positioning this bracket on the faceplate the correct distance from center, which I can verify with an edge finder. I can tweak the position of that until the edge finder tells me via the DRO that the distance to center is correct. Then I put the DTI on it and I get this bracket square to what will become the axis of swing of the bracket. This is variable number 2. So I tap that square just like tramming in a vise. Feed it while you tap, and I'm doing the chase the needle method where you just keep tapping in the known direction until the needle stops moving. You don't care what the reading of it is, you just want it to stop moving. Once that's straight, I can go back and check it with the edge finder again and make sure that it's the correct distance from center, and go back and forth if I need to move it until both of those 2 things are true, that the bracket is square to the y-axis of the setup and the distance to center is correct. Once I'm happy with that, then since it's on the mill anyway, I can just drill and tap the faceplate at these positions for the clamping bolts, and then I can get rid of the strap clamps that are holding the bracket. I can also still adjust it a little bit if needed. Those are clearance holes. And do one more check with the edge finder to make sure my distance is correct, and that looks good. One more check to see that it's still straight, and it is. So we are cooking. Remember that weird cylindrical T-bolt thing that we parted off of our own Mandrel? That is now going to be used to clamp the part to this L bracket. You can see it's got a little bit of space on the back there, so it'll clamp tight on the brass. I'm going to put that on there, and you can see that it's sitting in a slotted hole. And this is how I isolated that 3rd variable, because now I know those first 2 are correct, and I can now slide the part back and forth as needed to get the part centered on the x-axis of the setup so that it's swinging correctly. I'll use the edge finder to find one side of it, and I know the radius of the part, so that tells me how far off of center the center of it is. Then I can use a dial indicator on the edge to move it in the correct direction, the correct amount to get it on center, and then I'll double check that with an edge finder once again at the end. So this part is now square to the spin, the correct distance from center, and it's the correct offset, or it's centered on the axis of swing. As one final sanity check, I put a pointer in there and I check it against the scribe mark on the top, which shows me the final position of the top of the curve that we're going to cut. That distance should be correct according to the DRO, and it is, so the setup looks good and we can get it off of the mill. Now we need a counterweight to balance this, so I've got an offcut of that angle iron, and it's larger, but maybe includes roughly the weight of the brass part as well, and it'll be close enough. I've got these strips of lead that I typically use for counterweights on the faceplate. Yeah, they're not really enough, I don't think. So the other great source of counterweights for lathe setups is your change gears, because they're pretty heavy. They come in different sizes, and they already have a hole in them for bolting to things. Super handy. So those 2 gears plus the hardware that I'll use for clamping is very, very close, so that should be good. There happens to be a threaded hole on my faceplate, roughly equidistant from center straight across, so this should be a really good counterweight. Let's get that over on the lathe now and check our clearances and our balance and so on before we start trying to make cuts. Spin that up gradually and just see if it's going to vibrate. Actually, the balance on that is really, really good. I spun that all the way up to 500 RPM, which is faster than it's going to need to run for this radius of cut, and it's perfectly smooth. Lathe doesn't mind that at all, so that worked well. Let's go ahead and check clearances now with the boring bar that's going to make this cut, and here the news is less good. You can see that when I get to partway through my cut, that gear is definitely going to hit that boring bar. So that is no bueno. I got to move that counterweight further out or further out of the way somehow. I decided to split the counterweight up. I've got 2 other threaded holes that are further away but not directly across, so but they're sort of equally spaced across, if that makes sense. So I split the counterweight in half and I lessened it a little bit because they're further out, so they need to be lighter. And that was pretty good. I was getting some vibration there, but I did a little bit of adjusting using the clearance holes in the gears, and that seems to be pretty good now. It's not as good as when I used the scale and got it perfect, but yeah, it's good enough. And more importantly now, I've got plenty of clearance around those weights, so that boring bar will definitely not hit anything. So we should be ready to make cuts. With a tricky setup like this, I'm always going to take a really light cut first of all and just make sure everything looks like it's behaving as it should. So I do one very light cut across the part after touch off, and then we'll inspect and see if we see anything alarming. Well, the news is so-so. You can see that the outer cut is actually wider than the inner one, which should not be the case. That suggests that the outer edge of the part is leaning in a little bit. It's closer to the cutter than the inner surface is, which suggests either the bracket isn't square or the front and back of the part might not be parallel to each other. So I started doing some inspection, and honestly, I couldn't find anything wrong. The inner surface of that looks perfectly square to the faceplate. So I'm not going to start changing things because honestly, I can't find anything wrong other than what that cut showed. So that cut might be off for other reasons. It might have been a little bit of deflection in the cut, or it might be because a very light initial cut will sometimes exaggerate errors due to unimportant reasons like surface irregularities, things like that. So I thought I'll take a couple more cuts and see if it starts to straighten itself out. And if so, then I won't worry too much about it. In this case, fortunately, that is indeed what happened. After a couple more cuts, everything looks very, very straight now. Those cuts look quite identical to my eye, at least. Certainly good enough for what this is going to be. So I think there's no need to change anything. I want to be very sure that there is a problem before I start messing with a setup like this, because as you saw, it was a fair bit of work, this setup. It's not something I want to redo if I don't have to, and it doesn't look like I need to, so I'm just going to YOLO it. To be on the safe side, I kept the cuts light and I did lots and lots of passes. That just eliminates a lot of variables then if you're not stressing anything too much in the setup. I'm also using the heaviest boring bar I have because this is a very interrupted cut. And with an interrupted cut on a boring bar, the part is swinging around and it's banging into that bar every time, and it wants to deflect that bar a lot. So lots of light cuts, which, gives you time to work on your dance moves. Machinist dancing is all about keeping your hands away from the machinery while keeping one hand on whatever lever is critical that you flip in case something looks like it's going to crash. It's worth pointing out that this is one of two major ways that this would have traditionally been done before the CNC era. This way, or doing it the other way, fixturing the part on the cross slide and running a line boring tool in the spindle. For concave surfaces, you kind of have both of those options as opposed to the convex one we did before, which pretty much has to be done in some sort of spinning setup. This method worked great for me though. Using the mill as kind of a cheat for speeding up the setup really helped a lot. Now, that is looking pretty good. Let's get the smoke box in here and test it. The math says that I should be pretty much there. The layout line suggests I might need one more cut, but I never trust my layout lines too far, and sure enough, that is looking really good on there. I'm not sure I want to take another cut. I did a whole bunch of inspection in different areas of the shell, mainly where it's going to be sitting, and I used a light to kind of shine around in there. I felt around with my fingernail, just trying to see if there's any gaps anywhere or any way that this fit could or should be improved, but honestly, I couldn't find any reason to kick that out of bed, so I am going to leave well enough alone. Stop right here, even though it looks like my layout line might want one more cut. The finish on there is very smooth to the touch. It looks a little noisy. There's a lot of tool marks on it, again, because of it being an interrupted cut with a boring bar. The boring bar is dancing around a bit, but as I say, it feels perfectly smooth. Just a little bit of fun optical noise in the surface, created by the crazy physics of machining in a setup like this. Well, I think I can take it down now, which I always do a little bit heart in throat, because if I missed something or needed to take one more cut, now I've lost the setup that was pretty difficult to achieve, but I think we're okay. I'll take that over the bench. I'm going to have to deburr that before I can get that plug out because of how close fitting it is in there. You can also see now why the top of that plug was so thin, the top shoulder, because of course it needs to clear the final curve that we cut, not the entire part. It looked thinner than necessary when we started, but now hopefully that makes some sense. All right, let's get the plug out of there and finally do our real test fit now on the smoke box and see how we did. This is always a tense moment, even if you're pretty confident in the result. But oof, look at that. Friends, Romans, country people, that is phenomenal. I love that. Yeah, that has really come out nice. cut like that is always challenging, even though the principle of it is very simple and the setup is, as I said, a standard one that machinists have been using for 100 years. When you got to do it yourself, it's still tricky. But I'm very happy with that, and I'm very pleased with how that's looking so far. Unfortunately, that is all the time I have. This was a one-part week, pretty complicated setups, a lot of setup and not a lot of cutting, as it often happens with tricky parts like this. But please join me again next time. Thanks to my patrons for making all of this happen, and we will see you next time. Well, you'll see me because I'm on camera, but I can't actually see you because it's video, and that's how YouTube works.